Hello and welcome to the latest webinar by Big Gardner. My name is John Kowalski. I'm part of the marketing team here. I'd like to welcome you. Today's 60 minutes presentation will be on dispersion. It'll be a deep dive into that process. If you are unfamiliar with kind of how we run things, there's a chat box located in the bottom right-hand corner of your screen. Feel free to drop in any questions, comments, thoughts, in there. Time permitting, we'll get to them. If we do run out of time, we'll have someone follow up with you directly. We are also recording this presentation, so immediately following, you'll receive an automated link to that recording. Feel free to check it out later, share it with colleagues, whichever you like. Our presenter today, Mr. Andy Stumer, he is Managing Director of our VMA Getzman product line for US and Canada. It looks like he just dropped off here. Let's see. All right. He just got kicked off for some reason, so we'll see if he comes back. Andy, you there? Oh, he is coming back. I'm on mute. You there?
Hello.
Hey, good to see you again.
Hi. I'm at a hotel, so I got disconnected here for a moment. I apologize.
No worries. I just did the introduction. It's all yours, sir. Take it away.
Thank you. Welcome, everybody. I appreciate you tuning in today. So we're talking about dispersion process part 1. It's about the pre-dispersion process, which is really critical for the first step before we actually dive into milling, which will be our next segment here in a number of weeks. I think John will send out an invite for that also. Okay, so we're going to talk first about, I'll give you guys a brief introduction about VMA and the relationship with BIC. And we're going to dive into the dispersion process. We talk about different types of lab equipment as well as production equipment that is used today and what we offer. And then a segment about quality control. And then finally, we're going to close it out with talking a little bit about the lab capabilities that we have at our VMA dispersion lab at BIC USA up in Wallingford, Connecticut. And here you can see already on this slide, we offer everything from small-scale laboratory all the way pilot to manufacturing. There's a lot more equipment. This is just a snapshot kind of showing you the line of what we offer. Okay, so VMA Getzman is a German company, was founded in 1972 in Germany by this beautiful couple up on the top right, Hermann and Elke Getzman. They're still alive. Hermann is actually still visiting the office once a week just to make sure that everything is run smoothly and they still follow his design philosophy. The company is run today by his 2 sons, Martin and Christian Getzman. They're located about 30 miles east of Cologne. If you're familiar with Germany, it's kind of in the center of Germany and a beautiful part of that country. Big Gardner, or BIC, has had the exclusive distribution rights for North America since 1988. So almost 40 years ago, this relationship started. Like I said, the company is still owned by the same family, and they have over 100 employees worldwide. And they are known to make really high quality dispersers, different types of bead mills, basket mills. A strong focus is on our basket mill systems, the TML, as some of you probably are familiar with. And then we offer everything from lab scale pilot all the way up to production. Here you can see on the bottom picture that was the very first Dispermat introduced in 1973. There's actually some customers that we know that are still running on the original with the original motors. So these are very well-built systems, and they will run for a very, very long time. Okay, So here is a picture where you can kind of see the facility. So the building in the middle is actually what they added on. Here is additional capabilities for design of the equipment, as well as the manufacturing part. As I said, they're in over 100 countries. They're very flexible to different requirements. There's a lot of different new end-use markets. Just take batteries, for example, with specific requirements, and they're very adaptable to these new demands in designing custom pieces of equipment. So the facility is really state of the art. So if you ever happen to be in Germany and would like to stop by and take a visit, please let us know and we can arrange that. Okay, so obviously dispersing comes out of the coatings world. That's where it's really born, is to break up these agglomerates. And there's different types of pigment classes we look at. So we have the organic pigments, inorganic pigments, functional pigments, and then obviously the metallics, which are the special effect pigments. And they're used to really break down these agglomerates and make these binding forces, separate them, and turn these particles to a smaller size. That's the whole idea. The result should be that we have improved gloss, transparency, color, textural strength, cleanliness of shade, among some of these attributes. So we are dispersing in order to produce better wetting, break up these invisible, almost electromagnetic forces that hold these particles together. They're called the van der Waals forces. We like to ideally reduce the particles back to the primary particle size, which in turn will give us improved color strength, improve our gloss, give us an overall better appearance. We can save money by improving our pigment efficiency. We need less pigment because we increase the surface area if we do a proper dispersion. And that will help us also reduce the raw material costs, which will then also give us better product consistency, help us with the formulation improvement, and also result in a better particle size distribution, which in turn, if everything is right, should also give us really good upscale results when we go from lab to pilot all the way up to production. If we don't properly disperse our pigments, then we're going to have some issues. Among those are obviously color shifts, poor stability of our color, pigments flocculate back together. This can also be remedied with the right additive package, which our sister company Big USA is offering. Sagging, leveling, and settling are some of the other issues that come up. Our gloss will be diminished. And then also the separation is another problem that we see if we do an improper dispersion of our pigments. So it's really important to keep in mind that, in order for us to, when we reduce the particle size and we do a proper dispersion, it's really important that we have good stability. Pigments require strong color fastness to reduce fading over time. Our brightness will be improved dramatically, so this will give us also a much better color. And then pigment size, obviously, the smaller the pigment particles, our transparency would improve, we get better color. And then, like I said earlier, we can reduce costs by using less pigment, which helps everybody out when we go to market. And then also viscosity. Usually, we look at trying to keep the viscosity on the lower end. That will give us a better particle size distribution and helps us with processing of the material. If the viscosity is too high, it's very hard to move the material and break up these agglomerates. Also, if the viscosity is too low, then it's very difficult to put in enough energy and the process will just take longer. But viscosity is very critical when we process our slurries. So critical here is we're not destroying any particles. We're really just looking to breaking up these binding forces. And we are only basically reducing the size by separating the particles and not destroying them. And the agglomerates and aggregates are basically reduced to the primary particle size. That's the whole goal. And it's really the shear forces. We're using a Cowles blade in the dispersion process with the teeth that help us put in enough shear. And that is really the responsible component for that separation. And then, as I said before, we need to also look at the right additives to help us keep these particles in a suspended state once they have been separated. This is a good picture here, just giving you a quick look at the different types of pigments. Just you can see the yellow, the Pantone Hello Blue, just some different pigments here. So on this picture, you can kind of see what's going on. We have that larger, that's where you see that circle on the bottom. These are like these blocks. These would be our larger particle clusters. We call them the agglomerates. By using a Cowles blade, we are able to put in enough shear force to take these agglomerates and reduce them to the aggregate level. If we want to go from the aggregate level down to the primary particle size, which is a single block, that would mean that we would need to do the milling. That will basically get us from the aggregates down to the primary particle size. But what we talk about today is actually going from the agglomerates down to the aggregates, which will be done via the Cowles blade. So the idea is here wetting of our solid particles, the mechanical breakdown of the agglomerates and aggregates into the primary particle size, and then the small particle stabilization via the additive package. Here on this slide, it kind of lays it out really well. You can see with the Cowles blade, we wet our pigments, and then we break up these binding forces, and these agglomerates are turned into the aggregates. And then when we reach about 10 to 30 microns, depending on the formulation and the pigment type, is when we actually start the milling process. And then we want to keep those particles in a suspended state in our slurry so they don't flocculate back together. Same slide again. This is a great slide. It kind of shows you kind of the breakdown. We start always with the dissolver blade when we pre-disperse. And when we reach, the rule of thumb is there about 10 to 30 microns of particle size is how low we can get with a dissolver blade. Anything smaller, we really need to look at the milling process, which will be the next segment in a number of weeks. But we can go to about 10 microns with the dissolver blade using a disperser or a dissolver. So one key point here is when we use a dissolver disc, we always want to look at tape speed. So RPMs are critical, obviously, depending on the size of our disperser and the diameter of our blade. So RPMs are only one part of the equation. But what we really need to look at is we need to calculate the tip speed. And to have a proper pre-dispersion, to put us in the right window, we need between 18 to 25 meters per second of our peripheral speed or the tip speed, which is the speed of our blade spinning. And for that, we use dissolvers. So we have the SC line for our production, LC, and CV and CN and AE for our lab scale and pilot scale. And when we talk about fine dispersing, milling, or grinding, our tape speed will be lower, 10 to 16 meters per second of our milling disc or rotor. And there we have a variety of different instruments. So the vertical bead mills, our APS for the lab scale, basket mills, where we have a system called the TML. We also offer that with a quick change system for our production scale, where you can use a dissolver and then turn it very quickly into a basket mill. is something we offer seamlessly, not only for production, as you can see here with the SC, but also with all of our smaller laboratory machines. And then horizontal bead mills are also used then if you really need to go and reduce particles below 500 nanometers. Horizontal bead mill is required. And there we have a whole range, the RS series and the SL for our lab, which I will show you later. Okay, when we start dispersing, we have a container, and we always need to look at the ratio blade to our container. And the rule of thumb is we start out with about 1/3 the diameter of our blade to our vessel. That's optimum. That's if we have a medium viscosity, anywhere from 3,000 to 5,000 centipoise. If our viscosity is lower, we want to decrease our blade diameter. If our viscosity is higher, we want to increase our blade diameter to keep the product moving. You can see right there on the right side is a chart, and that kind of shows you on the bottom the different container sizes in milliliter. And you can clearly see that there is not one blade that fits every container. So we have actually a range. If I take a 1 liter container, which is about a quart, I can use a 30 millimeter blade all the way up to a 70 millimeter blade, depending on the viscosity. So if my viscosity is super low, almost like water, I would use a 30 millimeter blade. And then as my viscosity increases, I would then use a different blade diameter, a larger blade diameter, all the way up to 70 millimeter. So you can see there's quite a range, but the rule of thumb is optimum is about 1/3. That means also that the viscosity and the mill base has been optimized to get a good, proper dispersion. And then this is an important formula about the tip speed I mentioned earlier. So we calculate that diameter of our dispersion plate by RPMs and times pi. If we want to calculate meters per second, I divide everything by 60. But I would also express the dispersion diameter, the blade diameter in meters. So if I have a 50 millimeter blade, I would calculate that with 0.05 times, let's say, 3,000 RPMs times 3.14 divided by 60. That will give you the optimum or the actual tip speed for those RPMs and that blade diameter. And again, you want to reach between 18 to 25 meters per second, which is optimum for the pre-dispersion process. Then we have this visual cue. We call it the donut effect. It's really a phenomenon that if I have the optimum tip speed and viscosity, I should see the appearance of a donut being formed inside of my container. This is actually a really good looking donut right here. And that's what you really want to see when you optimize the process. Of course, if your viscosity is lower, or let's say almost like water, or like 500 centipoise or less, it will be more difficult to actually achieve the donut, because the donut would immediately collapse as soon as it's being formed, because there's just not enough viscosity. And if the viscosity is too high, then you probably won't see a donut either, because the blade would spin in there and it just never really gets to form the donut because it's so thick. So this really is an optimized dispersion batch, somewhere around 3,000 to 5,000 centipoise, and you would see if I'm running between 18 to 25 meters per second, that beautiful donut would show up. So that's what you really want to see. But it doesn't mean that you're not dispersing. If your viscosity is low, you just don't see a donut, but you're still dispersing. You may need more time to break up these agglomerates, or change the blade diameter or the amount of energy you're putting in. But you're still achieving a pre-dispersion if you run 18 to 25 meters per second. On this picture here, it kind of shows you where we break up these binding forces. And it's actually, if you take a look at this, if I have a dispersion blade, I have these teeth, what some people call it cowl's blade, right at the edge or corner where my teeth are located is where I'm actually breaking up these binding forces and separate these particles. On this picture, what's missing is actually it would happen, the same effect would happen on the bottom also, not just on top. So it would actually be on top and on the bottom of the blade. And that's where the shear forces are the highest. And that's where that separation of the binding forces will take place. Here again, you see a nice looking donut. We are putting in about 850 watts of energy, and our tip speed is 21 meters per second, which is optimum. Again, 18 to 25, that's kind of like the area we want to be in. And in this case, we're putting in 850 watts of energy. Everything looks really good, and we are properly pre-dispersing our material. And then we have the case where our tip speed is optimized, but we are only putting in 320 watts of energy. In this case, what's happening, our viscosity is very low. And that means it's more difficult to put in the energy. So what that would tell you is that you will probably disperse a little bit longer or change to get the desired result, or you would probably want to look at maybe adjusting the formulation to increase the viscosity so that you're able to put in more energy for reaching a proper pre-dispersion. So this is actually where the donut is having a difficult time being formed because there's just not enough viscosity right there. Okay, so that would be an issue. You could try to increase somewhat the tip speed, but it would probably be better just to look at the formulation and see if there is an adjustment that can be made to increase the viscosity somewhat to allowing us to put in more energy. And then we have the issue I talked earlier where we don't have any donut effect. In this case, our viscosity is very high. Doesn't mean we are not dispersing, we just don't see a donut because we are still putting in 900 watts of energy, which is really good. But we just don't see the donut due to the high viscosity. So if anything, you may want to look at maybe lowering the viscosity a little bit to put it back into that optimum window. But it doesn't mean that you're not dispersing. It's just that you don't see a donut in this case. But if I look at the amount of energy you're putting in, 900 watts, pretty good. And then you're running at 21 meters per second. So you may be able to make some adjustments to the tip speed, but this right there is a prime example of a very thick material. Okay, so in order for us to optimize, John, I see always there is with your mouse, the marketing instruments. Can you move that out of the way?
Oh,
it's
sorry.
always
There you go.
popping on the screen.
Sorry about that.
A little bit like a fly always flying in front of.
Sorry. All right. Fly is gone.
Right.
Continue.
Okay. Thank you. So in order for us to optimize the dispersion result, we want to look at the duration of our pre-dispersion. Again, the donut effect, that visual cue that we're looking for. Tip speed, really critical, 18 to 25 meters per second. Geometric consideration, meaning the ratio blade to container. Again, if the viscosity is higher, we want to use a larger blade. Lower viscosities, we want to reduce the blade diameter. Different types of impeller discs available. You can see on our website, there's a whole range, different arrangement of teeth and just designs, also different types of materials. Some people prefer ceramic, DLC coated, or so on. So there's a whole range of different impeller discs. The amount of mill base, so we recommend about a 50% fill rate in the container. You can go up as high as 70%, as low as 40, but 50% is what we aim for. Anything more than 70% usually gives you, spilling, will lead to spilling. That's not good. And if you are too low, then it's more difficult to oscillate. So, you don't want to hit the container bottom. We actually have some safety devices that will stop you from hitting the container bottom. But if you don't have enough mill base, you're not able to, position the blade in the right location. It's hard sometimes to move it up and down. So try to aim for about 50%. So 1 liter container, I'm looking for about 500 milliliters of mill base, up to 700 milliliters. Pigment and filler concentration, obviously formulation related. When we are dispersing, with pre-dispersing, it's not as critical as when we are milling, but we do put in quite a bit of energy. So you would see a rise in temperature. So it's probably critical that you have vessels that are jacketed that allow you to maintain a certain temperature. So we try to be on the lower end, especially when we're running with solvent products, to have the ability to really cool our mill base. Otherwise, the temperature will just rise very rapidly, and we want to avoid that. And then again, additives are critical to give us better wetting and dispersing effect, and no flocculation afterwards, so that the pigments stay in a suspended state. And then the next step would be, once I reach my 10 to 30 microns, that's when I would actually start the bead milling process. So it's critical to distinguish between the two different processes. So when we use a dissolver with a Cowles blade, we're only able to put in a limited amount of energy. That's just because we're only working with the blade. We don't have any media, no beads. That means our shear forces are going to be somewhat limited, and we are really only deagglomerating our larger particle clusters. We are not really breaking down the particles to the primary particle size. So we're kind of stopping at the aggregate level. If I want to take the aggregates and go down to primary particle size, is when it's critical to start the milling process. And it is a critical step for the entire dispersion process. So you can't go and take your material and then go straight to a media mill. That would probably lead to clogging of your screen or dynamic gap, and then you're not going to have any flow of your material. So it's very important that you first pre-disperse before you start the milling. And then again, as you saw earlier, you're going to have problems with the quality of your product. If you only pre-disperse and you don't mill, you're going to have poor color development, insufficient gloss, those issues, cleanliness of shade, lack of transparency. So that's all going to be related back to just using a dissolver blade and not milling. When we are bead milling, we're going to be able to put in a lot more energy with the beads and the rotor. That will really help us go from the aggregate level down to the primary particle size. We can go with the horizontal bead mill well below 100 nanometers. Certain applications require it. It's no problem, but you have to really use the right media size to really get you down there. And that will then give us the best looking product. So also helps you save money, because then you create more surface area, which in return will help you cut back on the amount of pigment that you're putting in your formula. And it will give you better color strength, better transparency, and overall better particle size distribution when you properly mill your material. So here's a picture of the lab scale dissolver. In this case, we're looking at an AE model. Here we have a number of different safety features. We have the working area adjustment. So we call it H1 and H2. So if you look at that container, We can actually set a threshold for the upper limit and the lower limit. That means that you can safely operate the disperser with the blade in between those two reference points. We call them H1 and H2. So let's say somebody were to pre-disperse and you run, let's say, 10,000 RPMs, for example, and you were to lift the up button, then the blade would stop at the upper reference points that you would set depending on the container size. So that means that there would be no moving parts really outside of the container, no product splashing around your lab, and nobody would get hurt by the blade spinning at 10,000 RPM. And then on the bottom, we also can set the threshold so that the blade would not hit the container bottom. It's also important, you don't want metal scraping, so that's really critical. So the H1 and H2 are standard with our laboratory dissolvers, with the series, the new CV3 Evo, and then also our CN model and AE flagship model that you can see right there. Depending on the size, we can go all the way up to about 20,000 RPMs. And then the beauty with the Dispermat, as I mentioned earlier, is that modularity, allowing you to basically fit different attachments onto the Dispermat, turning this dissolver into a vertical bead mill, either with an APS system or use a basket mill attachment, or even a rotor stator, allowing you then to actually emulsify if that's something that you want to do. So one equipment is designed for many different applications. We also offer explosion-proof designs. Some cases that's required, and then we have software available. So with our C technology package, you're actually looking at a C control panel right there. You're able to extract or export the data into an Excel sheet or CVS file, a CSV file, and then you can look at the data that way. You also have the ability to look at a chart. So that's graphing all these different values, and then you can see a trend line for your speed, your energy input, your torque value, and your temperature. So it's really helpful, and the C technology allows you to do that. And that is available also for not only the lab scale, for also pilot and plant size models. So the this Dispermat, our dissolver line, again, can be used as a homogenizer, where you mix, you can use a propeller blade, a butterfly stirrer blade. You can use it as an emulsifier or as a disperser, where you actually really break up these invisible forces, these van der Waals forces, with the cow's blade, and then convert it over to a mill. So depending on the attachment that you put on there. This is a great picture kind of illustrating what I just talked about. So on the top right, so in the middle, you see the Dispermat using the cow's blade for pre-dispersion. And then you have on the top left, you can see the rotor stator attachment. You can see on the top right, a vacuum system attachment. Some people like to remove air that's entrapped in their slurry. On the bottom right, we have the APS system, which is our vertical bead mill or like a pot mill attachment. We have a wall scraper system available for really viscous materials. And then on the bottom right is the famous TML, which is our basket mill version. That is very popular because it scales really nicely from laboratory scale to pilot all the way up to production. We have this quick change system. You can if you look at the shaft in the middle, right below the motor, there is a clamping ring, and that whole assembly, you remove the clamping ring, you turn the assembly, the shaft assembly 180 degrees, and you can pull out the shaft and then replace it with any of these attachments that you're looking at, except the wall scraper system. But it takes less than a minute, and the dissolver will turn into a rotor stator or a milling system. So just giving you a quick overview, I don't want to spend a lot of time on that. We have a whole different range of dispersers. So for laboratory scale, very small volumes, something very simple, easy to use. We have our LC line, no real bells and whistles. It does have the safety features, but basically you are looking at a control panel that just shows you the speed and a timer function. That's all there's to it. You would lift the motor up and the shaft manually, so you can see there is a lever on the right side of the motor, and that you turn that, and then you can lift the motor up and down the stand, positioning at the right height. On the smaller scale model, like the LC, that's really easy to do because the motor isn't that heavy, and so you can it just slides really nicely up and down, and then you can position it where you want the blade to be. You see the wheel on the right side of the clamping system, right above the stand. So that actually is used to loosen and tighten the container clamp. So it's very important that the container is always clamped absolutely tight so that it doesn't wiggle around. You don't want it to move and then the blade hitting the container wall at very high speeds. That's not good, especially when you're running with solvent products, based products, and you always want the blade to be perfectly centered. So that will help you really center the blade and make sure that it doesn't get in contact with the container walls. And then we also offer an explosion-proof version with our LC line, the LCEX. This is the new innovation this year. It's the CB3 Evo. It's replacing the standard CB3. It comes with the CV control panel, which is almost the same as the C control panel. So be able to look at your speed, your energy input, your torque value, your timer function. You have a temperature readout. On an advanced model, we offer a basic and advanced version. The advanced will also have the integrated scale, which allows you to take measurements, and then you can actually see the measurements on the display, which is really cool. On the advanced model, you can also track and store all the data. So if you want to look at that later on, or you want to create a lab report, so the advanced model is designed to help you do that. This is really good technology for scaling up. So if I want to, use all the data and I want to go from lab to pilot or production, then these are the values that I'm looking for. Also, it'll give you the actual tip speed displayed on the top right of our control panel, which is the critical value we're looking for, 18 to 25 when we are pre-dispersing. And then if I put a basket mill on here, I'll be able to see the same values, but then I want to be running at 10 to 16 meters per second. I can't say that enough because the question always comes up: how fast are we running our disperser? What are we looking for? Or if we are milling with the system, what are we looking for? Very smooth up and down of our motor. So it's hard, it's almost like a Rolex. You don't really see any jerky movements as you're moving the shaft up and down. It's got the container clamping system, again, all fitted with the safety features. So if the container was loose, the machine would tell you on the display, and then it wouldn't even power on. You will have to tighten the container with the wheel, and only then will the machine give you clearance to actually start running. And then if the container is clamped properly, then you're setting H1, H2, which are the reference points I mentioned earlier for upper and lower limit. That means that you can then safely operate the disperser in between those two reference points. If you were dispersing, or the blade would be outside of the container, outside of these limits, then the machine would also show you that on the display you're not safe and you cannot run the machine. It will not even power on. So very cool design. Brushless step motor, extremely quiet. We had one at the battery show. We ran it at 20,000 RPM and people couldn't believe it. They could hardly hear the machine running. They're like, this is unbelievable technology. So if you are looking for adding laboratory scale capability, It's a good time right now. Let us know, and we can send you more information on this awesome piece of equipment. Then we have the CN line, which is kind of our bread and butter instrument for small to medium-sized batches. We can also upscale that to pilot. Has the CN control panel, giving you also your speed. It'll show you the torque value. It'll give you a temperature readout and a timer function. Again, all the safety features are built in, as I mentioned earlier, but the beauty of it is that it's scalable. So you can see here, you're staying within the CN line, but now you're looking at a pilot scale model. Again, same brushless step motor technology, even on the larger models. They are really, really quiet and there are hardly any vibrations to the motor. So the shaft goes straight into the motor. There are no belts or O-rings or anything like that you need to replace. So they're practically maintenance free. And we have customers that are really running on the original Dispermat motors for over 30 years. I've been with the company for 18 years now, and I've never seen a broken motor. So speaks for the quality and the design. Just a really, really, really well-built piece of equipment. Then this again is the AE with our C control panel. That's like the flagship model that we have, especially useful for upscale. And we also offer pilot scale models in the AE line. So very cool. You can basically create batches. You can store the data. You can give batches a name, either by product name or actually by product number. You can upscale really well because you have all the data. You can see on the display the actual trend lines for each of the values. During the dispersion process, you can do a net power calibration, which basically means that you can set all the values to a 0 point when you're running without product in the beginning, because obviously as the machine is spinning, the motor is turning, the shaft is turning, it's already using energy. And by doing a net power calibration, you can set that value to 0. That means that all the values are only related to your product, like the energy input or the torque value. So there is no influence from the machine itself. So that would be the net power calibration feature. You can program cutoff values, meaning if you have a temperature limit, you don't want to, let's say, exceed 80 C, then you can program the machine to cut off once it reaches 80 C, or and give you warnings before. So there's 2 different warning stages. You can program, so you can say, I want to be warned at 70 C and at 75 C, and at 80 C, the machine will turn off or run with a different speed or different energy input. So you can really customize it the way you think it works best for your process. Ideal for the laboratory and upscaling process. It's very easy to extract the data, goes right into an Excel sheet or a CSV file, so you can do whatever you want with the raw data. So that's really helpful, especially when you want to create lab reports or you want to upscale. And then we have explosion-proof models as well. Here you can see, John, your cursor is again right in the middle. So there is explosion-proof models. We can go all the way up to 31 gallons of mill base. Ideal for scale up, if I want to go to production. Again, because we're using the C technology, we can do the net power calibration. We can program these cutoff values. We can set up the machine to run not only with a certain speed, but also with the amount of energy we want to put in. That means if I'm running with, let's say, with constant power, then as the viscosity changes during the dispersion process, my machine would automatically adjust the speed to always maintain the amount of energy that we are putting in. And then fully programmable, and then again, explosion-proof models are available, not only lab scale, but also for the pilot scale models. Then we offer a whole line of production dispersers. So you're looking at the Dispermat SC. We can go up to about 2,000 liters of volume. The beauty of it is, again, fully modular. We have that quick change system. We can very quickly fit a basket mill on there, meaning I'm buying a dissolver, but let's say I want to also mill with the same machine. I get the quick change system, and now I'm milling with the basket mill. It's perfect. So I don't need to buy multiple pieces of equipment. Everything, dispersing and milling, can be done on one machine. Some people require vacuum, so that's also an option with the vacuum cover and the vacuum container. We can pull out the air for better dispersing and milling effect. We can also add nitrogen if we want to create a nitrogen blanket or argon gas for some new end-use market applications like fuel cell development or batteries. So that's also an option. The cover is removable, so you have access, for cleaning. And then certain materials that are very viscous require wall scraper systems, so that is also an option with our production scale machines. And then again, explosion-proof models are available. Here's an example of the vacuum production scale disperser. So basically, by running a vacuum, we can have an improved wetting and dispersing effect. We're taking out all the air, meaning we can put in more energy. If you think about air bubbles, they can act like tiny little air mattresses, buffering the blows, or they're causing the shear force. So that means by removing the air, I can put in more energy. Also, that eliminates any type of foaming. So if I want to be able to, transfer from the container to another container, air is the big enemy. So by removing air, I have a much better transfer efficiency from one container to another container if I'm pumping out my material. So that means I have much faster product transfer, improved homogenization, cost savings. I'm going to be doing everything quicker. So there's different types of vacuum pumps that we offer depending on the container size and how much vacuum you need to pull. And then again, we have the option of adding ports for nitrogen, argon, or any other type of inert gas you may want to use. Quality control. So quickly on the left, you can see the C control panel giving you your speed on the top left. Then right below in watts, the energy input, 2,380 watts right there. Right below that, we have an indirect measurement of our viscosity in terms of torque. On the top right, we're actually showing you the tip speed, 25.4. Temperature readout, 42C. And then on the bottom, we have our timer function. Then the two windows on the top right corner, you can see H1, H2, which is the safety device for our reference points, container reference points, and then the container clamping safety system right below. They would blink, actually they would light up green when they are operational or the machine is in safe mode. If one of those two is not in a safe state, it would appear red and then would make basically you wouldn't be able to turn on the machine. We offer that for the lab, pilot, as well as manufacturing size machines. And then on the right side, we have a very simple control panel. We call it the M technology for manufacturing. Some customers prefer really simple in the manufacturing environment, a little bit more sophisticated for the lab, but we offer both options. And then obviously, here is a PLC controller made by Siemens. We work with that company, giving you the flexibility of doing your own programming and maybe integrating that system to your entire workflow process. If you want to add a scale, a load cell, or anything like that, they can all be programmed, and then that would be the ideal solution for that. Here is just a snapshot of the control capability with the C technology. So, for example, we have a blue one, just give it a name, and then you can program how much energy you want to put in. In this case, we have 5,000 RPMs. We're not running with constant power. Then the diameter of our blade is 50 millimeters. The container size is 1,000 milliliters. We're using H1, H2 settings. So the height is 80, the bottom is 5 millimeter. The actual disperser blade height would be 14 millimeters. The timer is set to 45 minutes. And then we have on the right side the cutoff values for all of our different indices. And then we have the graphical interface. Actually, these are pictures from an older version of a C controller, but you get the idea. You can actually look at the trend lines for each of these values and watch the dispersion process in real time. So if you see a spike, for example, in temperature, then it will show up right there, and you can say, "Hey, what's going on?" Or if you're running with constant power, and then your speed would obviously increase, meaning that your viscosity is dropping, which we would also probably see that on the torque curve. But it's really nice that you can see all these different values on display very easily with the C technology. The net power calibration, I already explained that earlier, that you can set the machine to a 0 point in terms of the amount of energy you're putting in. So that means when you're running it, that all the values are really related to your product and not any machine input. That is the WinDisp software we offer. We're actually moving away from that for the new models because we feel it's easier to do all the data tracking in the Excel sheet. So that is actually something we are looking at. We still offer the WinDisp 7, but I think personally that with the Excel capability and the transfer, it kind of makes it a lot simpler. But here you can see also the training and everything can be done in the WinDisp software. We have an applications lab in Germany at VMA, obviously, where you can come and visit and we can do trials. If you happen to have a facility over there or you just want to come in for a visit. And we also have a nice lab in Wallingford. We actually have a lot more capabilities. We're adding a new vacuum dissolver. We have a horizontal bead mill. We have the new AE, which you can see right there. So some of the newer machines out there. So if you have any application that you want to really test out with a basket mill, for example, a vacuum system, let us know. We've been more than welcome to have you up there and take a look at the equipment capabilities. So the Wallingford lab really is state of the art. It's at Big USA. One of the big advantages of having it up there with our sister company is that we can leverage the synergies between the instruments and the additive business. And I can't stress that enough. It's always important that you have somebody on site that understands formulation. So if you're looking at, selecting equipment and having somebody who also understands the additive packages that help with certain formulations, how they relate to the instrument, that can be really helpful for also from an upscaling perspective. So we don't look at ourselves as somebody who wants to sell you just a piece of hardware or a dissolver or a bead mill. We want to really help you make the best possible product with, including everything from a support angle, also selecting the right additive package for your formula if you need that help or assistance, and then test it out how it works on our equipment. So that's some of the big advantages of having the lab up at Big USA and working with our colleagues hand in hand with our customers, giving you the best possible solution. If you just want to come in and look at the equipment without actually running a trial, you're more than welcome to come up there. We'll spend a day with you to walk around the facility, show you everything. We can also use the time to do a seminar, what we did today, maybe more in depth even related to your product. So let us know, but we've been more than happy to welcome you at the facility. So this concludes the presentation today. Thank you very much.
Yeah. Thank you, Andy. We appreciate it. Thank you for the expertise. Out there, folks, I did in the chat put in a link to register for part 2 of this series, where Andy goes into a deep dive on the media milling side of things, the next part of Dispersion. So with that, I'd like to thank you. Thanks for joining us. Hope you learned something. I know I always do. If you have any questions, I know Andy's running tight to another appointment, but if you have any questions, simply hit reply to any of the automated marketing messages you receive, and we'll route it to Andy and his team and get you taken care of. So with that, thank you, and we look forward to seeing you on future Big Gardner web seminars. Thanks and have a great day.